Start. All right. Hello, everyone, and the people on Zoom. I think we have Stephanie. Welcome to our first club workshop. My name is Phuc. I'm the club president, and this is Stanton. He's the secretary. So today's workshop, we're just gonna do the overview. I'm gonna talk about definitions, just some basic breakdown. Talk a quick run over of different types of binary tree. I'm gonna do a BFS breakdown, DFS breakdown, and under DFS, it's gonna have inorder, postorder, and preorder. And then at the end, we're gonna do Q&A session if you have any question, and then we're gonna do example problems live. We can do it as like a whole group. I think it's more fun that way. So quick definition. Let me move this out of the way real quick. So binary tree is it's a hierarchical data structures. So you always have, it has different nodes, and every node has a value. It can be a number, string. Every node has up to 2 children, left and right. So different types of nodes. So we have the root of the tree is like the very top node. The parent is any node that has a children. The child node is any node that has a parent. Sibling are nodes that share the same parent. And then the leaf node is the nodes that are at the bottom of the tree that doesn't have any children. And talking about code implementation, this is what a tree class looks like in Python. We have class tree node here. Define init, data, left, and right. Data is just like what number it holds. Left is the left child, and right is the right child. Any questions so far? Yeah.
So for all the left children, you have to be less the value has to be less than
no. No, actually no. So this is a normal binary tree.
Okay.
What you're talking about is actually a binary search tree. So that's a different. So we're gonna go into that. Yeah, that's a difference between regular tree and binary search tree. Yeah. And yeah, so that's just the definition of tree. And then so next we're gonna move on into different types of tree. Honestly, you don't really have to memorize most of these. Hey, welcome in, Chris. Hey, how's it going? Welcome in. Yeah, we're just like going over the slides and different types of tree right now. So so I'm just gonna do a quick run over of the different types of tree. You don't have to memorize any of these. I barely see these being asked during Leetcode or OA anyway. Yeah, I don't think I've ever done most of these. So full binary tree is a tree that every children has 0 or 2 nodes. So no like single out edges. So for example, this one, this node has 1 children, so it's not a full binary tree. Nobody gonna quiz you on this, so don't even worry about this. Complete binary tree, it's filled up. So all the nodes are filled up, all the levels are filled up until the end. Yeah, perfect binary tree. What is? Yeah, it's that. Balanced binary tree. Okay. And then this is the important thing that that's like actually important. So yeah, so binary search tree, the definition is that all the left subtree of a parent of a node has to be less than the current node, and all the right tree right here, all the value right here has to be more than this node. And it applies recursively for every single node. So if you look at 6, 4 is less than 6, 7 is greater than 6. So left child has to be less than the current parent, right child has to be bigger. For number 8, left child is less, 3 is less than 8, 10 is more than 8 because it's on the right, and it has to be the same for all the subtree of lefts as well. So like if you have a 9 here or under any tree of 3, it's not going to be considered binary tree, search tree. So why do you guys think is important? Like, why do they have to set it up that way? Like, why do they have that rule to like have all the left subtree to be less than the current node and all the right tree to be more than the current node? Like, what's the significance?
Because it's not balanced, you can't search through it in log n time.
So yeah, so if it's not a binary tree, so if you want to search for like say 6, you have to scan the whole tree, and that could take time, right? It's going to take ON time, so you basically have to scan the whole thing. However, if it's binary search tree, so like say you're searching for 6, you start at 8, you know that 6 is less than 8, right? So it cannot be on the right side, so you don't even bother going down the right side. You just go straight to the left side because you know, oh, 6 is less than 8, it has to be on the left. So that's the significance of that. So it's really efficient search log n time here. So for search, insert, and remove, here's a quick breakdown of the different runtime. ON, O log n. So you can see it's a lot more efficient compared to regular binary tree. So that's like the takeaway here of binary search tree is it's really efficient. Any questions so far? Okay, it's good. All right. All right. So like I said before, when it comes to solving binary tree problems on LeetCode, there are two main traversal method, BFS and DFS. Most of you are familiar with DFS and BFS, right? I assume. Okay, no worries. So BFS is you traversing the tree by level. So if you look at this tree right here, it's going to travel the node. So this one is considered the first level. The second level is 2 and 3. The third level is 4, 5, 6, 7. The fourth level is 8, 9, 10. And that's how it travels. So basically level by level. 1 and then 2, 3, 4, 5, 6, 7. Does that make sense? Yeah. Straightforward. It's just layer by layer. So it requires a queue for keeping track of the nodes, travel level by level. Okay. I'm just gonna do a quick showcase of the code. So this is a LeetCode problem that utilize BFS. So given the root of a binary tree, return the level order traversal of its node value from left to right level by level.
Or the first one.
I'm gonna do BFS, so iterative with a queue. Yeah. Results equal array. Then while queue size equal. So the reason why I know to write the code, because like this is something you just gotta memorize and be able to. Yeah, I'm just gonna do it real quick. So
Doing the iterative one or the first one?
I'm gonna do BFS, so iterative with a queue. Yeah. Results equal array. Then while queue size equal. So the reason why I know to write the code, because like this is something you just gotta memorize and be able to come up with on the spot, especially during interview.
I think I've always thought that you can stack. Yeah. Yeah. Like I would push the first of your own, and then pop it and then get all of the use a stack for this? Yes. That'd be very long to stack. Well, no, never mind. You'd have to take track of the level you're on. Be best using. you're doing depth first search, it's not gonna be useful, but if you're doing breadth first search like this stack would be exponential.
Okay, should be almost done. I hope that works. Let's see, what can we do? Oh, well. So this is like the template of BFS. I can like save it into the slide so you guys can access this later, like memorize this. Like this is like something you should be able to like come up with during OA. Okay, I'm gonna move on real quick. So that's BFS. It basically what the code does is gonna print the node by level. You gotta go.
Yeah.
All right. Go for it.
See everybody.
Yep. And then, yeah, so that's BFS. So next is DFS. And so this is like some, DFS is like more popular compared to BFS. Will you guys agree? Yeah. Yeah, when it, especially on Leetcode. So there are three things that are categorized. So we have pre-order, in order, and post-order. So the way pre-order works is you process the current root and then you process the children. For in order, you do left child, the current root, the current node, and then the right child. And then for post order, you do the child first and then the current order. And out of all of these, pre-order is the most popular, I think. In order is really only used in binary search tree. And post order is also popular. Yeah, I would say I've seen it used a lot. So I'm gonna do a deep breakdown here.
I think we should comment on like, you know, in order gives you.
Yeah, I have more here. Yeah. So, all right, so pre-order first. So again, pre-order, so it's process the parent first and then the child. So for example, if you look at this right here.
If you hit more, you can hide that. Then you high floating media controls.
Nice. Okay. So when you run the code, it's gonna do current, and then left and right. So when you first pass in pre-order of 20, it's gonna do 20, and then the left of 20 is 15. So it run the code on 15, which start at 15. And then run on left, go to 12, and then it go back. Okay, here we go. All right. Perfect. So yeah, this is kind of like a bad example, but you can see it's printing out pre-order traversal. So it go to 1 and then 2 and then 3. Maybe if we have a better test case. So for example, if the tree is something else, 1 here. So where?
So hover over run code or that.
Oh, I mean, you know what? Just take it forward. You just take it on. It'd be better if you just take it on.
Okay, here, I'll just make my own real quick. Here. 1. Yeah. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And what this looks like is like this. Perfect. All right. And I'm gonna run my code. Okay. So this is pre-order.
So it's 1, 2, 4, 8, 9, 5, 10, 3, 6, 7. Okay, cool.
On the roof. Like all the left nodes.
Yeah.
And
So,
goes notches off to the right.
So it goes, it's doing 1, 2, and then go down to 4, to 8, and then it go back to 9. And then for number 2, it go down to 5, go to 10. So this is all done. So go back, up to 1 again. So 1 is done, it goes to the right, which is 3. 3 go to the left, and then go to 7. And if I change the code a little bit, so instead of that, I can put it in the middle. So what do you guys think this is? If it's in the middle? Huh?
You had it right.
You had it.
It's an
It's in order.
inorder.
Yeah, yep. So run code.
So the tree is gonna be eight, you know,
Actually, 8 donuts. Or donuts will.
Yeah, go for it.
what was the order that we did?
In order.
8 for, scroll up. For bringing them down.
Screw. Okay, but like you guys get it, right? Yeah.
Yeah.
Okay. So just in order, pre-order. No. So that's a, I think there's a member in there. And then this is, so this is like the most interesting to me, root.val post order. Okay, so this one is doing the leaf first, basically the children first. So it's kind of like bottom up. Yeah, so as you can see, it's doing the leaf first. Come on. It doesn't let me drag. Oh, yes. Okay, so this one, as you can see, right, it's going 8, 9, 4, and then 10, 5, and then 2, and then it goes over here, go to 6, 7, 3, and 1. So it's basically bottom up. Is going from the leaf up to the top. Okay, so just to show you like the live code.
The reason why it's post is, you know, the root of the
Yeah.
parents on the last.
So let's do some quick example right now. Okay, so post order. So when to use post order? So when we want to inspect the bottom leaves first, any problem that require you to see the children, process the children before you can make decision about the parent first, then you use post order. And one example of this is this problem right here. So this one is a medium. So given the root of a binary tree, return the same tree where every subtree not containing a 1 has been removed. So for example, this tree right here, and the return result is like a new tree that any subtree that has a doesn't have a 1 will be removed. I'll let you guys think about it for a little bit.
This is post order traditional.
Yes.
Can you check the recording real quick? I think I turned it back on, but. Okay.
It's recording.
All right.
So yeah, so okay. Right off the bat. So everybody understood the problem though? Yeah, okay. So yeah, so this is example 2, right? So this tree, like basically all the tree that's like all 0 has to be removed. So if you guys, one thing you guys notice that all the stuff that's like being removed or the leaf like start from the bottom, right? You always remove from the bottom first. Like you don't start with the root and you remove it. You start from the bottom. So if you do DFS with let's say pre-order. So if you do parent first and then children, it's not gonna work. What you want to do is you want to do, so okay, I'm just gonna jump in it. So I'm gonna define a helper function that takes in a root.
Just name it like BFS.
So the logic, I guess the logic is like you look at any given node, right? You look at the left child first, and then you look at the right child. to see if it's a non-one tree. And then same thing here to see if it's a non-one tree. So what happened if both of left and right is non-one tree? Well, you have to check the parent first, right? So if both left and right is non-one tree, then you only prune when the parent is also 0, because if the parent is 1, then you have to keep the parent.
Keep the child.
If both left and right is non-one tree.
Or right.
Oh yeah, so if left is non-one, then you prune root dot left, and then look at the right. If it is, then you prune the right tree.
Like, within binary tree, or are we like taking like a copy?
We are modifying the original, because if we make copy, it's going to be not space efficient. Yeah.
At this point in time, space efficiency really is.
Mhm. So if left and right is non-one tree, well, actually we don't. Yeah, so and then we will check if parent or current node is 1. If it's 0, then we return false for the function, because this is a non-one tree. Return false. Else we return, oh, I mean return true here. Okay, so what is this traversal right here? So as you can see, right, we call the function on left, we call the function on right, and then we use the information from left and right to make decision on the current parent. So that is Postorder right there. So left, right, and then current. So that's Postorder. So let's code it. Let's see. Left equals the result, right? So we call the function on left, which is root dot left. And I guess up here we got to do if not root. This is make case. Return true. So if left, then that means we have to prune root dot left. So root dot left equals what? If we prune it. Yep. And then same thing, we look at the right. So right equals helper root dot right. Prune it. So we're gonna do if right. We prune it. So root dot right equals none. If both left and right is non-one. If left and right. If the current node, so root dot val equals 0. So that means left is non-one, right is non-one, current is not 1. Then obviously we return true. That means that's our result right there. Else return false. And that should work. Let's see. We call helper of root. What do we return here? Root, I guess. Yeah. All right, let's just see if it works. Of course. Anything else? There we go. All right, submit.
a tree of nothing.
Wow, I have two cases off. Okay. Why is it not working?
Tree is empty, you return null. You're not putting the tree is empty.
Oh, we return no. Okay, so if not root, return none. Is that it?
Well, that.
After pruning. Yeah, that's like after pruning. Please wait. Please wait. Fuck. Return.
You can just do what you did in the helper at the end. You forgot to make the helper equal to something. Your helper is returning a value. So if not helper,
Okay.
then
So if not helper, return none. Is that it? Well, we're close enough. Anyway, we gotta move on. The show must go on, guys. So that makes sense though, right? So that's an example of post order. Any question? So how do you recognize it's a post order right there on that particular problem? I'm sure it's just some random bug somewhere. We got almost there. We're past most of the test case. So how do you recognize that this is a post order problem?
because we have to get the children first.
Yeah.
This would also work as a file.
Yeah, so that's pretty much it. Like any problem, and if you can just look at most of the example here, that you can see, right? Like all the stuff that we remove, most of them are leaf node, and they are worked on from the bottom up. So that's that right there is giving you a way that is a post order traversal. Okay, no questions. All right, next one is in order. Oh, wait, that was post order. Okay, we skipped pre-order. So pre-order. So this one is a little bit easier. So this one, instead of processing the children first, we process the current node first, before going down. So here's another example. This one isn't easy, so it's a lot easier than the previous problem. So maximum depth of binary tree, you just given a tree. Your goal is to find basically the height, the maximum height of this. So the intuition is that if we do depth first search, it should work, right? So we start from the top and we just keep on going until we hit a leaf node, then that's our value right there. And then we update the thing. The really, really cool thing about this problem is that you can use post order on this, or pre-order, or even BFS. Like most traversal technique works on this problem. Like I could come up with like 3 ways that this can be done. So it's a really, yeah, it's a really cool way to like showcase a different method. So okay, here real quick, I'm just gonna do the, so this is gonna be post, what is it? Pre-order. So that means parent first, then children. So what we want to do is like we have a result equals 0. Then we define DFS, takes in a root. So basically what we do, so remember parent first. We're gonna check for base case is when it hit the leaf. So basically we keep traveling until we hit the leaf. And then height as well. So if root, if not root dot left, and not root dot right, what is that checking right there? What is that line checking right there? Yeah, it's checking for the leaf node, right? because a leaf node doesn't have any children, so that's checking for the leaf node. So the idea is like we want to keep traversing until we hit the leaf node. Then that means we know that it's the end of the depth, right? So when we hit the so if we get there, then we update the maximum value. So height. So yeah, so one way to do that is you have non-local keyword. If you put it there, then you will be able to access your thing. Okay. Mm-hmm. And then
We're doing functions.
root dot left, and then the height is +1. And then DFS root dot right, also height +1. Okay. And then we just call it DFS of root, and then the first height is 0. So the counter, so height is like the counter of where the level it's at. So when we go down to a children, we increase the level by 1. And then we just return return result. Now we run code. None type. Oh yeah, no check. If not root, return. Yeah, just return. We don't need to return anything. Oh my god. What?
I think you're excluding your root node. So if you start out with your root,
Your high.
God.
and so your result should be.
It just if not root.
Well, no, it should be 0.
I think they can do that. But
Oh yeah, yeah, you're right. Yeah, yeah, you're right. Should work. All right. Maybe. Yes. Okay. Yeah.
17%.
So I think like one optimization is if you utilize backtracking, right?
Mhm.
Because like let's say like in the middle of your traversal, you found the maximum depth already.
How do you know that?
Oh, sure, you were.
Yeah, we don't know unless we travel every single node. Yeah. So that's an example of top down or a pre-order. So the reason why it's a pre-order, so as you can see here, right, you process the current node first, and then you call the children, DFS on left and right. Any question? Does it make sense, or how do you guys feel? Okay, good. So as I mentioned before, can you guys think of another way to solve this? So this is pre-order, right? So it's going down from the top. Like, can it be solved bottom up? From the bottom to go up?
Yeah.
No pen?
You bet.
I mean, there's something to try.
You would, well, if you want to do it, you would have it go all the way
Thank
to
you.
the bottom, and every time it returned, it would return 1. And so once it reaches up to the top, you would have the parent have the maximum amount of children, or know the children under it.
Yep, yeah. So actually the
The other way we would get this.
so the bottom-up approach of this is literally 3 lines. It's really cool. I'll show you. So, huh? Yeah, it's freaking cool. I didn't think of it. I saw a solution on Leetcode. So so this solution is going to be Postorder. And remember, what is Postorder? It's going to be children first and then parent. So that means we're going to have to call children first. So call function on left, call function on right, and then we make the decision from there.
Oh, we would just continue up once the children's children are only, okay, never mind, cool.
So result equals something, right? So process parent.
No, yeah, that's what
Version, my favorite. Algorithm. Good call. Iteration. Employee Chevron.
Root dot right. Actually, I'm just gonna write down res equals maximum of left and right plus 1. Return result. That's it. Oh, no check. If not root, return 0.
Can you show the whole code real quick?
So I can condense it down to 3 lines as well. I'm just writing it out so that it looks easier to understand.
Go over to left and go over to right. And once it's both children are 0, then we start returning up. And as we go up, we're just going to keep on adding 1. Now we use the max function. I would have done it differently.
So this is the intuition.
Max.
So like, if you're at this node right here and you're trying to find the max depth of this, you just find like, what if you already know the maximum depth of this and this? If you already know the information of the children, so like say this is the max, the depth of 3, this has a max of 4, right? So if you know that your left children has a depth of 3, your right has a depth of 4, then the maximum, including this one, is going to be 4 plus 1, right? So that's the intuition. So this is 4. So you pick the maximum of the children, and you add 1 because it's 1 level above. So that's the intuition. Yeah. So that the same thing for what's it? Postorder, bottom up.
I think the light inclusion.
It's so clean. Yeah, I love it. It's just to showcase a different approach of preorder and left order. Okay, and then next we have inorder. So this one, don't even worry about it. Like you only use it for binary search tree. You can't really use it on a normal tree anyway. But yeah, so when to use, mostly use in BST. Okay, so yeah, so here's a code. This is like the template. So for BFS, this is like what I memorized to use. I can send it out into the club so you guys can like copy and paste it. DFS, it pretty much is like no check. and then process the parent, do the DFS on the left, do the DFS on the right. It's just like the general pattern. It varies a lot, so you don't necessarily have to memorize this. This is BFS. I recommend just practicing more with BFS to get this down. But the thing with BFS is like once you get it, like most problems are pretty similar to each other. Once you get this part. So summary, you can solve most tree problem with BFS and DFS. DFS is a lot more popular. Under that, we have preorder, postorder, inorder, and I already demonstrated how each of those can be used to solve problem and when to recognize them. So yeah, any questions? We're at the end of the workshop, I guess. Go for it.
Oh, no, I don't have one.
Okay.
Next, what's the next topic are you gonna cover?
So what do you guys want to like do for next week? You guys want to move on to the next structure, or you want to keep doing tree, one more practice with tree, or anything, like could be like anything, graph,
I
linked list, array.
think a good structure would be tries. It's pretty much trees, but it's an extension,
Mhm.
right? But tries.
Well, the thing is like we don't see try in OA, so like maybe something more popular, I guess.
It's listed on code.
I guess. Yeah. I don't know how to do tries. It's yeah.
It's really cool because it uses hash maps